Let's talk about rotational spectroscopy. Rotational spectroscopy is an experimental technique in which you measure transitions between various rotational energy levels. We saw from the quantum mechanical treatment of a rigid rotator that we have quantized energy levels, and we know what the energies are. We recall that the energies from that treatment is L plus 1, h bar squared, over 2I, where L is a quantum number starting at 0 and going in integer values all the way up to infinity, and I was equal to the reduced mass times R, and the reduced mass, let's take a linear molecule, as we did it for. Linear molecule is atom 1 and atom 2 in the molecule. The reduced mass will be the mass of atom 1 times the mass of atom 2, divided by the sum of the masses, and R is the distance between the nuclei of the two atoms, or in other words, R is the bond length. All right, what the chemists decided to do in their infinite wisdom is to change notation here. So L, now the quantum number L is given the symbol capital J, and the quantum number M sub L is now given the symbol capital M sub J, and that's the quantum numbers we use. They're the same thing, but there's a quantum numbers we use when you talk about rotational spectroscopy. So with that change in notation, these are the energies of a rigid rotator, where it's just J plus 1 h bar squared over 2I. Recall the angular momentum was quantized in units of h bar. So here we have, instead of L, we have square root of J plus 1 times h bar. And recall that the z component of angular momentum was also quantized in terms of h bar. The quantum number here is capital M sub capital J. J can go from 0 on up to infinity in integer steps, and M sub J could be 0 plus or minus 1 plus or minus 2. Okay, so with that change in notation, we're ready to look at rotational energy levels. And remember that the energies are 2J plus 1 degenerate. In other words, for a given value of J, you can have 2J plus 1 values of M sub J, each one of which is the equal in energy. Although we won't consider this, let's nonetheless go beyond a simple linear molecule. So if you have or actually a diatomic molecule is even better. Okay, so we started here with a diatomic molecule. What happens if you, say, have these are different atoms? Let's just say H2O, or for instance, if you have, that's a two-dimensional molecule, or if you have, say, methane. All right, that's a three-dimensional molecule. How do you treat the rotational motion of this? Well, in general, you talk about rotational axes. And those rotational axes are axes that you have separate and distinct rotational moments of inertia. Okay, so you would say, okay, this is a rotational axis here, and so on. So, and those may be different from symmetry axes. All right, so in general, if you have a three-dimensional molecule and it's not linear, you would have three moments of inertia pointing along three different directions. However, if the molecule has a single moment of inertia, then it's called a spherical top. If it has two moments of inertia, it's called a symmetric top. And if it has three moments of inertia, it's called an asymmetric top. Let's just introduce these two terms here, oblate and prolate. You can get a symmetric top by starting with an ellipse. Here's an ellipse here. Ellipse is described by two axes. One is the minor axis, and the other is the major axis. If you rotate around the major axes, what you generate is a cigar shaped in 3 dimensions. If, on the other hand, you rotate around the minor axis, what you get is a disc shaped. They look the same, don't they? Oh well. But I hope you get the distinction there. So these ellipsoids of revolution, as they're called, are two distinct shapes. In one case you look like a disc, a flying saucer. The other case you look like a cigar. and those are symmetric tops. And then if you don't have that, then you have an asymmetric top. So that's just a generalization. But what we'll consider exclusively here now is linear molecules. Okay, and there's one more change or one more nomenclature idea that we have to get. So if you have 3 moments of inertia, you have 3 values of h bar squared over 2I, A, B, and C, corresponding to the moments of inertia along A, B, and C. And you call h bar squared over 2 times the moment of inertia A, where A is the smallest moment of inertia. You give that the symbol capital A. And then rotation around the one that's in between the smallest and largest, given the symbol B, and the one, the largest moment of inertia, rotation about that, h bar squared over 2I, that's given the symbol 2IC around that axis, give the symbol C. Okay, we're considering linear molecules, and for some strange reason, the chemists have decided to use the symbol B. So remember, E was h bar squared over 2I, and linear molecules have a single axis, a single moment of inertia. You can only rotate around the bond axis, and that was J plus 1. All right, and this the chemists are going to call B. So that's equal to B, J plus 1. So that's another change in nomenclature. So the quantum number went from L to J, and M sub L to M sub J. And now we're combining these terms, h bar squared over 2I for linear molecules, and we're going to call that B. All right, with that, we can maybe go ahead and look in more detail at rotational spectroscopy.